So we've been talking about variables of distance and time and how they relate to an object's velocity. So in this video, we're trying to answer the question, how do we build an equation that represents the relationship between distance, velocity, and time? So the first thing we need to do is decide which of our variables are dependent variables and which are the independent variables. So if you think about the three variables that we're talking about, distance, time, and velocity, which one is dependent on the other two? When we were making our distance time graphs, we decided that it was distance that depended on the time and the velocity an object was traveling at. If you think about the distance that you're able to travel while you're walking, your distance is going to depend on how fast you're walking and for how long you're walking. We want to be able to predict the distance that an object is going to travel. So in order to do that, we need to make an equation that's going to act like a moving object. And in order to do this, we need to figure out what variables have relationships and whether these relationships are linear or inverse relationships. We're going to start looking at these relationships by looking at a basic distance-time graph like the ones we've made in class. So this is a graph that is showing an object traveling at a constant velocity of 0.5 kilometers per minute. We know that it's traveling at a constant velocity of 0.5 kilometers per minute because we can look at the slope of the line. So the slope of the line is indicating the velocity. So what kind of relationship is this between distance and time? Is it linear, inverse, or some other kind of relationship? So take a minute to think for yourself, what kind of relationship does this look like? So hopefully you concluded that this was a linear relationship between distance and time. And how could you figure that out? Well, for starters, it looks like a straight line. Another thing that we see is that as one variable goes up, the other variable is also going up. So if we look at time of 2 minutes, for example, if we look at 2 minutes, at 2 minutes, the distance up here is at 1 kilometer. If we double the time to 4 minutes, our distance should double as well. And if you read the graph correctly, you'll see that the distance does double. So as the time doubles, the distance doubles. And that's a clear indicator of a linear relationship. Next, we're going to look at the relationship between distance and velocity. So let's say you want to see how much distance you can cover in a constant time interval of 3 seconds at a range of different velocities. We've created the graph on the right for you to show this relationship for our fictional data set. Remember that velocity means how fast you're moving in a particular direction. So is the relationship between distance and velocity a linear one, an inverse one, or some other kind of relationship? And how can you tell? So similar to the distance-time relationship, the distance-velocity relationship is also linear. Again, you can tell because it's a straight line. You can also tell by as you increase the velocity, you're increasing the distance you can travel in an interval of 3 seconds. So when the velocity is 2, your distance you're covering is going to be 6 meters. If you double that to a velocity of 4, that means you're also going to be doubling the distance you cover to 12 meters. Now that we've figured out what our relationships are between distance and time and distance and velocity, we're going to combine these relationships into an equation. So we are going to assume that the only two things that influence the distance you travel are the velocity that you travel at and the time over which you travel. And this is true. So we're going to start by putting our dependent variable, which is distance, on the left-hand side of the equation, and we can put our independent variables, velocity and time, on the right-hand side of the equation, because distance and velocity have a linear relationship. They can go on either side of the equals, and time and distance also have a linear relationship. So we're going to multiply the two independent variables over on the right-hand side. So we'll have d equals v times t. So this makes sense because as we double velocity, we're going to end up doubling what comes out on the distance side. Also, if we decide to triple the time that we're traveling for, that's going to triple the distance that we cover. If we decide to say double the velocity we're traveling at and triple the time over which we're traveling at, we are going to increase the distance we travel by 6, because v times t equals d. If v is 2, t is 3, we're going to go 6 times as far, or 6 times farther. So before we start using this equation and running with it, we need to test it to make sure that it makes sense and that the answers it produces make sense. So let's look at the following scenario or sample problem. So we're going to say at exactly 12 p.m. a football player was located at the 20-yard line. So can we find what her velocity is using our new equation? So it's true we have a time value and we also have a distance value. And we're trying to find her velocity, but we don't really know what she could be doing. She could be standing still. She could be walking backwards. She could be standing there digging a hole. So we don't have quite enough information in order to calculate her velocity if we just know her time, the time at which she's standing there, and her position. So in order to make this equation more robust, we're going to need to add some operators. If that first equation that we came up with wasn't going to work for our problem, what do we need to do in order to make this equation make more sense? So this is the full velocity equation that we're going to be using in this class, and you can see there are key similarities with the equation that we just came up with. You can see there's a d for distance on the left and a v for velocity on the right, multiplied by a t for time. The key difference here is that we've added operators, which slightly change the meaning of our variables. So we would read this as delta d equals v average times delta t. So why are we using delta d instead of just plain d? Well, if we're trying to find velocity, we don't care about a particular spot where somebody is standing. We care about how their distance is changing. And the delta operator indicates change. So we're looking for their change in distance. Why v average? Well, we're looking for their average velocity because velocity can speed up or slow down. We're trying to figure out over a certain interval what that velocity averages out to. And why are we using delta t rather than just regular t for time? Well, it's not so important to know at what time the football player was standing on the field, but we need to know the starting time and stopping time of her motion. So we need to know the change in time, how much time has gone by, in order to calculate velocity. So when you're working on problems in this class, it's really important to pay attention to the operators. So the little symbols that we're attaching to our variable symbols, because they mean different things than just the letters alone. So you may need to calculate the delta D or delta T on your own when given a set of distance or time values. And this is simple because we're just looking for the change, but pay close attention to the notation. So to summarize what we've covered today, we determined that the change in distance has a linear relationship with an object's average velocity and with its change in time. So this is the equation we're going to be using relating the three variables. It's really important that you pay close attention to the operators in this equation. Delta D is very different value than D initial or D final, so we don't want to get those all mixed up. You'll get very wrong answers if you use the wrong variables, so pay close attention to the operators that we're going to be using.